Welcome everyone, my name is Nicholas Lane and I lead the Machine Learning and Systems Lab at the University of Cambridge. It's my pleasure today to present on behalf of the team shown on this slide. We wanted to take this opportunity of the Google Federated Learning Workshop to present an early preview of some tools and analysis that we've been working on over the past few months. Now, the heart of this talk will be a description of an open source federated learning framework that we have named Flower. In particular, Flower makes it simple to perform some important forms of system-orientated research within the domain, and although it's in early stages, it's ready to be used and contributed to. You'll find documentation, code, and a white paper describing Flower available at the URL flower.dev. Now, in this talk, I'm going to be presenting results that have been produced using Flower, and closing out the talk with some preliminary results that judge the carbon footprint of federated learning in comparison to central learning in data centers. So we want to be able to use Flower to judge the environmental impact of these two different types of machine learning. Now, it's still early stages for federated learning, but already there has been some key ideas produced. There's some fantastic systems up and running, but one area where this field lags is in the way that we typically evaluate our algorithms. What you're being shown here on the left-hand side is a code snippet that's illustrative of how far too many algorithms are being measured inside federated learning. Commonly, they're being judged as they execute on a single machine, where the various different types of federated learning clients are simply just members of an array as part of a fairly simple simulation. Now, there's a big problem in evaluating your algorithms like that, because we know even in modest-sized federated learning systems, real-world different types of system issues creep in to have enormous consequences to how these things actually behave. You might have federated learning clients where one member is perhaps even up to 1,000 times more powerful than the other. If you have a case of a flagship, latest and greatest smartphone contributing alongside a tiny embedded ARM processor, for example. These clients are going to be linked over networks. If they happen to be linked over wireless networks, we know that there are going to be fluctuations in speed and stability. There's going to be energy implications. So none of these type of factors are going to be accounted for in this type of evaluation. Now, this gets me to why we developed Flower. We developed Flower to be able to assess these different types of factors in a much more easy manner. Let me now discuss what Flower is by going through it component by component. But the key design principle of Flower is for it to basically sit on top of existing deep learning frameworks as a framework that does the federation above the deep learning framework itself. It's meant to be compatible with PyTorch, TensorFlow, and Keras, meaning that you can take training scripts that you've developed and then suddenly federate them by combining them with Flower. We think this type of approach is going to align well with how people are going to tend to build these systems moving forward, where they're going to select the different components that run on the different clients based on how well they're suited for the hardware and software support that's available to these clients. I'm going to now just very rapidly walk through the different components of Flower, but again, there's a white paper on our site if you want to read about more details. A key component of Flower is the client support. We have a Flower Client Sdk. You can implement Flower to run in terms of its client support on any different type of device through C++, Python, Java, and so on. You can take, as I mentioned, existing training pipelines that do not work in a federated fashion and link them in to our Flower framework and to federate them in a very easy manner. We've implemented off-the-shelf, well-known federated learning algorithms, such as FedAverage. There's 4 different types of core algorithms there and a variety of variations supported as well, or you can implement your own. Of course, we have the necessary servers to coordinate the contributions from the different clients. That's there. And we also want to promote more comparisons done on a systematic basis between people's algorithms. So we have examples of Flower being used for different types of machine learning workloads. We have benchmarks of Flower running different algorithms under different models. And importantly, we also offer what we call Flower datasets. Now, because there's no real accepted method by how we want to distribute and partition the datasets we train under these different sort of federated learning scenarios, we've taken it upon ourselves to partition datasets already known for things like speech and vision and NLP and split them across potential numbers of clients under principled rationales based on real-world evidence of how they might be spread across different clients. The idea here is to offer datasets that you might want to evaluate your algorithm against, and other folks can do the same. And by by measuring yourselves against the same different types of partition datasets, you can easily compare against each other. Now, I mentioned before and started this whole talk off saying that Flower makes it easy to assess real-world different factors when you're testing and experimenting with your federated learning setup. So let's go through those components now. One of the key issues is that scalability. There's not enough scalability when we judge our federated learning algorithms currently. Now, Flower can run on a single machine, no problem. It can also run on a handful of real devices that you might have in your lab. But sometimes you're going to want to experiment on 50, 100, maybe even 1,000 clients. And to make that easy, we've developed modules that can fit in and instantiate instances within cloud services. Currently, Flower only supports the Amazon AWS types of services, but it can be easily extended to other cloud providers. The idea here is that Flower takes away all the pain of instantiating some number of clients, managing their contributions, collecting the information, and judging how well the algorithm works. It's all automated for you, and allows you to scale to what is not normally seen in the literature in a very quick and easy manner through configuration scripts. Another factor here is networking and wireless. We have software simulators that can inject latency and instability in terms of the links that connect different federated learning clients. That's built into the system, as well as hooks into energy monitors that may be running directly on the devices that you could be deploying to, or in terms of software energy monitors that you might have attached to different instances that you've started for your evaluation. Now finally, compute heterogeneity in terms of also compute heterogeneity as well as memory constraints also need to be factored in. As I mentioned earlier, you can do this in a real-world setting by actually running these things on actual devices, so smartphones, Raspberry Pis, and so on, by implementing Flower Client Sdk APIs. Some cloud providers are also offering what is called device farms. So Amazon offers a device farm where you can actually get an instance of an actual smartphone and deploy a workload to that. We support this usage within Flower too, so you can have a mixture of Flower-based federated learning clients where the target are not just regular Amazon instances, but are actual real devices within a device farm built straight into the system. Now, here's a quick snapshot of the different types of use cases we think that Flower is going to be incredibly powerful for enabling. I mentioned the scalability. On the right-hand side here is a snippet of an actual configuration script. So within a matter of 20 lines, you can have Flower start 50 different instances within AWS to run your algorithm and test it in a real system where actual instances are exchanging real information. You can see all the different implications of your algorithm design. It's also possible to very easily do analysis of different type of networking, wireless, compute, and memory configurations using the components I've mentioned. Now finally, it might not be obvious from the way I've been describing the system, but it's completely possible to use Flower to run an actual functioning federated learning system if your interests really lie in building an actual application and study the application level questions rather than exploring system parameters. So you can use Flower to run any type of federated learning system you might want to consider. Now let's look at some of the code. These are just some 3 different examples I want to show you to get a feel for what Flower is like. there's three of them, right? So the first one, blue number 1, that shows a little bit of code that it's actually very little. That's the little code that's needed to be able to connect to an existing written Cura script that trains the model and wraps it inside the overall Flower framework, allowing it to be federated. Number 2 here, that's just a couple of lines I've used to illustrate just how little is needed to get Flower up and running. You'll need these 2 lines plus a configuration file and you're away. The third example and final is just illustrating what is it like to implement your own federated learning algorithm within Flower. Everything else can be left as is. You can implement your algorithm by extending this class and then just starting the server. Let me now examine some results that Flower has been able to produce relatively easily. I'm going to walk you through a pair of results. They've been deliberately selected to illustrate the implications of real-world system behavior on the performance of federated learning. Some of the results may be not that surprising, but what I'm really showing you is interesting system results that have been enabled very easily with the Flower framework. Let's focus on this first graph here on the left. It's Flower training a ResNet 50 architecture using FashionMNIST as a dataset. In this setup we have 10 instances participating as federated learning clients. Now each of these are Amazon instances. They have the ability to be to use either NVIDIA V100 GPU or the regular Intel CPU to perform the training. And what we really want to take a look at is on this y-axis the training time it takes to train this model. There are 2 types of experiments run. In experiment 1, all of these clients can use the training available on the GPU. Those are the red bars. Now in the blue bar, exactly the same setup, but one of those clients has been forced to run on the CPU. So they do their training on the CPU. So one of the clients, one of the 10, are much slower. And you can look what happens to the overall performance of the training. One client slightly slower, suddenly in the example I'm highlighting with this, I guess it's an orange arrow, we see its training time has jumped up 3.5 times. Now imagine what happens if you were not considering these type of factors when you're evaluating your algorithm. Let's move from what was an example of compute heterogeneity to that of memory, to network connectivity. Here we have the exact same setup, 10 clients within a pool. Looking at training time on the y-axis, x-axis, now we're varying the speed that these clients are connected. I'm going to illustrate here that there's a factor of 2.1 times increase in the training time from when we have the clients connected with 1000 megabits per second versus 30 megabits per second. So under the 1000 megabits per second, you can imagine this is the type of connectivity you would have within the data center or within a lab with a wide connection. The 30 megabits per second is more what you'd find on actually a fairly fast link such as a 4G connection. Much more representative of the speeds you'd find within federated learning, but you can see again, training time lifts enormously. And the main takeaway of those results is just really how easily we're able to have these very realistic system-orientated results under the Flower framework. Now, those are quite potentially eye-opening to some of you, but they're fairly predictable ways to measure federated learning. So this final example, what I want to do is we want to stretch ourselves in terms of showing you something new that you might not have seen before in terms of how you assess federated learning. We want to pick on the issue of carbon footprint. The reason for that is that there's this growing awareness within the machine learning community of the considerable environmental consequences of activities. We know that training, for example, a SOTA NLP model can potentially have just as much carbon footprint as a small US-based family over an entire year. So clearly this type of behavior is not sustainable, and we realized that these sort of questions had never been asked about federated learning, and Flower was the perfect vehicle to really explore these trade-offs between federated versus centralized learning, when is federated a good idea, and actually even just quantifying what is its carbon footprint. Obviously the methodology for this type of analysis is very complicated. It's very dependent on assumptions being made. So we have a white paper on our site that describes and walks you through our methodology. I'm going to very briefly highlighted 3 factors here. Factor number 1 is that we model the different types of key differences between the data center and the federated learning setups. Some of the key ones are that, for example, federated learning is going to spend a lot more carbon in moving data around because it's going to operate over a wider area network, whereas the data in the data center is traversing, just very short links, not much carbon being used there in terms of electricity. On the flip side, the big difference for data centers is that they use a lot of cooling. You're going to find that a data center is going to use maybe 30 to 60% of its energy just on cooling alone, and that's a factor that federated learning systems just don't need to account for. The second issue, shown in green, this is just highlighting that depending on where the data center and or federated learning clients are positioned, then the sort of multiplier that going from energy use to carbon output is going to be quite different. If you're in France, for example, they rely a lot on nuclear energy, so the carbon emitted is obviously a lot less. And finally, 3, flour is a big part of this situation because it allows us to have accurate measurements of things like wall clock training time under different federated learning settings. Briefly want to go through these results here. This is a toy result in some sense. The federated learning situation is very small, model's very small, data center is only 1 GPU, but it still produces a lot of interesting insights for us to discuss. So here we're training a ResNet 50, again under CIFAR 10. I want to focus on the table on the left here. This table here is comparing data center versus federated learning carbon footprint when you're training the ResNet 50 up to a 75% accuracy at different locations. Overall takeaway here is that federated learning has a larger carbon footprint of 3.4 times. Now again, please, this is tied a lot to our assumptions of the data center setup, the federated learning setup, and the carbon equations that we happen to be using. But again, it's a big jump, right? Federated learning is using a lot more. What are the data center assumptions? We're assuming a V100, single GPU, and this factor called PUE, which is power usage effectiveness of 1.67. So this is kind of the type of range of value you're going to see in, say, a university data center, whereas, big commercial data centers like Google, Amazon, etc., they're going to be around 1.1. On the federated learning side, the system is very capable. We're using Jetson TX2s. They use 8 watts or less. Credit card size, you'll find them in high-end IoT cameras. So it's a pretty powerful setup. We have 15 total participating to produce these results. Now, let's look at why this carbon footprint question and difference exists. And this is what this evaluation on the right-hand side is showing us. You'll notice that the data center slope of carbon emitted y-axis against the number of rounds at training times, and basically the amount of work done at training, the slope of the data center is much higher than the federated learning one, but it's because the data center can reach the 75% accuracy so quickly that its carbon footprint is so low. If I bring up the federated learning example, you see that it takes 150 rounds before it completes and gets to 75% accuracy, so much, much longer. Therefore, the carbon footprint is much, much bigger. This is a fairly unique way to look and judge and assess federated learning, enabled by Flower with this sort of carbon modeling on top of it, and allows us to do things like this. We can look at, well, what's the break-even point? At what level of efficiency of a distributed training would allow federated learning to break even with the data center? And we can see here it happens to be 40. This is a very rich way to start to assess algorithms, and we can think of things like, well, what's a mixture of methods that could help us reach this goal, not only by reducing the number of rounds required, but seriously advancing things like the speed of on-device training, perhaps coming up with some federated learning friendly architectures. And really the bigger message here is this is a through Flower performed analysis where you can judge different federated learning algorithms, used an example of carbon footprint to show how you can judge things on very atypical metrics that are very meaningful to the world, and then take into account the full spectrum of algorithm behavior in terms of how you'd also start to change these end outcomes by doing things such as changing the different federated learning configuration, or how powerful those devices are, how those networks connected and so forth, and really see how the whole thing fits together. I'm really low on time now, and so I just want to say thank you for listening. We're all very excited about this platform and the community that may want to benefit from it. Please let us know if you have any thoughts, insights, feedback. We'd love to hear from you. And again, thank you for your time today.